Hello. In this video, we will discuss the Riemann-Stieljes integral. Let me start with this question. The integral of function x squared from 0 to 1 with respect to variable x will be obtained by x cubed over 3 from evaluate from 0 to 1 gives us 1/3. Okay, that's a simple example of Riemann integral. But how could it be the integral of function x with respect to x squared from 0 to 1? Okay, so here, instead of variable x, we specified another function. Or in general, we're going to discuss the function f of x, the integral of function f of x with respect to another function, g of x. Okay, this is a typical form of the Riemann-Stieljes integral. So let me give you a definition of the Riemann-Stieljes integral. Here, the integrand is a bounded function. And another function g we assumed to be an increasing function. Increasing function on the same domain definition. Now, for specific partition P in this interval, okay, so the starting point A is T0 and T1, T2 to Tn, and the node in the point of the interval. For each partition, we're going to define the upper Stieljes sum. Okay, the upper sum when you develop the Riemann integral or the Riemann double integration, the upper sum has been defined by it has been denoted by mu or function f with respect to partition P. The summation is k goes from 1 to n to tk minus tk minus. Okay, that's the length of the interval from t0 to tn, okay, from tk minus 1 to tk. That's the length of the interval, or the increments of the delta increments of variable t. Okay, multiplied by the value of the function. Here we evaluate the supremum, capital M denotes the supremum on this interval from tk minus 1 to tk. Okay, and that's the upper double sum. However, we're going to define the upper Stieljes. Instead of delta t, here we're going to use the delta g and delta gk for the increments of function g on this interval. That means you're going to replace this part by g of tk minus g of tk minus 1. So this is the increments of function g on this small surface. And similarly, we can define the lower Stieljes sum denoted by, okay, for the upper Stieljes sum, we're going to specify the function that we evaluate the increments as a subscript. And similarly, the lower Stieljes sum denoted by Lg of f and p is defined by the summation as k goes from 1 to n. Okay, and we have the increments of function z multiplied by here, the value of the function f, the value of the integrand function f on this interval will be measured by the sup-imp, little m, and for the infimum of this function in the subinterval. Okay? So, in the Stieljes integration, the Riemann-Stieljes integration, you replace delta t by delta g, or delta tk by delta tk, gk. So instead of the length of the interval, we replace the length of the interval by the increments of function g. Then the rest of the development is almost the same, almost the parallel as we have done in the double integration. So we can define the upper interest integral and the lower interest integral. The upper integral has been defined by the infimum of all possible upper sums. The upper integral mu g of f. Okay, this is the upper integral of function f with respect to another function g. This is defined by the infimum of u, g, and of p for all possible partitions. And similarly, the lower Stieljes integral denoted by Lg of f is defined by the supreme of the lower sums or Stieljes sums. And we take the supremum with respect to all possible partitions. Okay, then the integrability will be defined by the equality between those two different integrals. Okay, the function f is now Stieljes integral with respect to g, okay? Or this situation will be simply denoted by g integral. The function f is g integral. That means function f is integrable or Stieljes integrable with respect to the function. If and only if those two integrals, the upper integral for function f with respect to g agrees with the lower integral. If that's the case, in this case, we define the integral of function f with respect to another function g. Or this is a simply simplified notation. So f of t is g of t. Okay. This will be defined either one, since they are the same. You can choose any, the upper integral or the lower. Okay, that's the definition of the Stieljes integral. So, the only difference from the double integral is this. Instead of variable, the increments of the variable, here we use the increments of the another function. And the rest of the development are very similar or almost parallel to the development of the double integral. For example, say suppose we have two partitions P and Q. And between those two partitions, we have this inclusion relation, which means Q is a final partition. Q is finer than P, or Q is what's called the refinement of the original partition P. If that's the case, we can compare the lower sum of function f with respect to g over the partition P. And when you get the refinement, we replace the partition P by another, the final partition, the lower sum gets increased. So lower sum of partition over partition P, another partition Q, the refinement gets bigger. On the contrary, starting from the upper sum over partition P, if we take the refinement, or if we replace the partition P by a final partition, the upper sum gets decreased. So the upper sum over partition Q has these inequalities. Of course, for the same partition, the upper sum is always bigger than the lower sum, since we use the supremum and infimum. And here we have assumed that the function g is increased. That means all the increments are positive. Okay, so we have this natural inequality between the lower Stieljes sum, and the upper Stieljes. Okay, and uh, For any partitions, P and Q, okay, they don't have any inclusion relation at all. For any partition, for different partition P and Q, you can compare the lower sum, lowest Stieljes sum over partition P, and the upper Stieljes sum over another partition Q. Then, for any combination of partitions, we always have this inequality. Okay, and I think all of you can remember the way to show this property for the double integration. What is that? Right? And G over the lower sum. And here we have the upper sum with respect to another partition. Then we can construct a refinement or finer partition, finer than both of them, by taking the union. Okay, so if you compute the lower sum over P union, by taking the union of two partitions, it's going to be a finer partition than P. So the lower sum gets increased. And similarly, the upper sum of F with respect to union partition gets decreased. And here we have the lower sum and upper sum for the same partition. We have this natural inequality. So all the lower sums, no matter what kind of partition we have, all the lower sums are less than or equal to all the upper sums. By taking the supreme, we get the lower integral. And by taking the NP of all possible upper sums, we're going to get the upper Stieljes integral. And the inequality is still valid for those integrals, which means the lower Stieljes integral is always less than or equal to the upper Stieljes integral, right? So lowest integral cannot exceed the upper Stieljes integral. But if they are different, we cannot compute the Stieljes integral. When they are the same, we're going to call the function f is f integral, or Stieljes integrable with respect to function g. Okay, and the rest of the properties are almost similar to the double integration. For example, G integrability can be stated in terms of the existence of partition for any epsilon if there exists a partition P. But then the upper sum, the difference between the upper sum and the lower sum gets closer than an arbitrary epsilon. Okay, that's an equivalent condition for the integrability or G integrability. Can you skip the proof? And there are quite a few sufficient conditions for the G integrability, Stieljes integrability. For example, if the function is continuous, then is a Stieljes integral with respect to any increasing function. And the Stieljes integral is also integral which has the linearity. Now, before I get to the linearity, let me first mention this property. Say suppose we have an intermediate value C between the in the domain of definition, which is the integral from A to B, then we can split the Stieljes integral of function f with respect to g from A to B into two different Stieljes integrals from A to B. We have an intermediate value C. Then the Stieljes integral from A to B can be split into two integrals from A to C and C to B. So the integral from A to C function f with respect to g plus the integral from c to b of function f with respect to g. Okay. Now we mention the linearity. Say suppose we have two functions f1 and f2. Both of them are g integral. And here we have another constant c. Okay. Then the Stieljes integral is also linear, which means the integral it to be of function c times f1 is okay, since it is linear, and this constant can be extracted out of the Stieljes integral c times a plus b, the integral from a to b of function f1 with respect to g dg. Okay, here before we mention this kind of property, when function f1 is g integrable, the constant multiple c times f1 is also g integral. And we have this kind of problem. Okay? And say suppose we have two g integrable functions, their sum f1 plus f2. The sum of these two functions is again g integrable, and the integral of sum of two functions f1 and f2 with respect to dg can be split into the sum of two Stieljes integrals from a to b f1 dg. From a to b, another function f2 dg. Combining these two properties, we have the linearity. Okay, the linear combination of two functions. Okay, or the Stieljes integral of linear combination of two functions agrees with the linear combination of their individual Stieljes integral. Okay, and we can verify this property again based on definition of the Stieljes integral. Let me get the proof. However, the Stieljes integral has another linearity, which is quite different from the linearity of the double integration. Okay, so the Stieljes integral is also linear with respect to the function g. That means, say suppose we have two increasing functions, g1 and g2. We have two different g's. They are increasing functions. Interval from a to b, and c is a constant. Then the integrand f is g1 integral. At the same time, this is g2 integral. So this function f is integrable with respect to two different g's. Then we're going to have the linearity with respect to z rather than f, which means the integral of function f with respect to d and c times g1. Okay, from a to b is the same as the integral or Stieljes integral with this multiplied by the constant c. Again, to claim this kind of inequality, we have the Stieljes integrability of function f with respect to c times b1. Okay, so function f. If function f is g1 integrable, this function is again c times g1 integrable. And Stieljes integral can be of function f with respect to sum of two functions, g1 and plus g2, can be split into the, the sum of two individual Stieljes integrals, which means this is the same as the integral of function f with respect to dg1 and the Stieljes integral of function f with respect to dg2. Okay? Again, to claim this kind of equality, we have the integrability. Function f. If f is g1 integrable and g2 integrable, then this function is integrable with respect to the sum of those two functions. And we have this kind of equality. Okay? So this is not the same as the double integral. Okay? We have the linearity with respect to integrand function. That's natural. The double integral also has that kind of property. But the Stieljes integral has another linearity. It is also linear with respect to the function g. So let's take a look at the proof. Let me just give you the proof of the second proposition. Uh, okay, let's pay attention to the upper Stieljes sum. Upper Stieljes sum of function f with respect to g is defined by the summation as k goes from 1 to n. We compute the supremum of function f on each subinterval multiplied by the increments of this function g, which means g of tk minus g of tk minus 1. Okay, now I'd like to compare this upper sum with respect to the upper sum of function f against the upper sum of function f with respect to sum of two functions, g1 plus g2. Okay, so let me replace this function g by g1, the sum of those two functions, which means for the supremum multiplied by g1 of pq plus g2 of pq minus g1 of pk minus 1 minus g2 of pk minus 1. And by collecting these terms, we're going to have the upper sum of function f with respect to g1. And collecting these terms to get the upper sum of function f with respect to g2. Okay? So the upper sum with respect to sum of two functions are the same as the sum of two upper sums with respect to individual increasing functions, g1 and g2. Okay? And this property also holds for the lowest. The lowest sum of function f with respect to g1 plus g2 can be split into the lowest sum of f with respect to g1 and plus lowest sum with respect to g2. Okay, based on this observation, I'd like to prove the integrability or Stieljes integrability of function f with respect to sum of two functions. To do that, let me start with an arbitrary epsilon. And function f is g1 integral, which implies there exists a partition P1 such that the difference between upper sum P1 and minus lower sum gets smaller than arbitrary constant. Okay, epsilon. However, I'd like to use half of epsilon. If we have another integrability, the function f is also G2 integrable. That implies existence of another partition P2. So the upper sum with respect to G2 over partition P2 and the difference between the upper sum and the lower sum. Lower sum with respect to G2 over partition P2 gets smaller than half of epsilon. Right? And by taking the union of those two partitions, P1 and P2, we're going to compare compute the difference between the upper sum with respect to sum of two functions over the union partition and the lower sum with respect to sum of two functions. Okay, then first we can split this upper sums and lower sum into the sum of two upper sums and lower sum. So this can be replaced by upper sum with respect to G1 and upper sum with respect to G2 and minus the lower sum with respect to G1 and lower sum with respect to G2. Okay. Then what if we replace this partition P by P1? Okay, here partition P1 related to the function G1. Okay, so if we replace this partition by P1, this P is a refinement, it's a union. So this upper sum gets smaller when you take the union, which means this part is bigger. This upper sum is bigger than previous. And similarly, we replace this by upper sum over G2 with respect to partition P2. Then this term is bigger than this. And so we have this inequality. We have claimed this inequality. Okay. What about the lower sums? The lower sum gets bigger, that increase if we take the union. So if you compare this with G1 and P1, okay, this lower sum is smaller, okay, less than or equal to the lower sum like this. But we have a minus sign, which means this term with a minus sign gets bigger than the previous. Similarly, this part can be replaced by the lower sum over P2. Then the difference between these two, upper sum and lower sum, is smaller than half of it. And the difference between those two, upper sums and lower sum, are smaller than half of epsilon, which means these functions are smaller than epsilon. Okay? So for arbitrary epsilon, we can construct a partition P, and with respect to this partition, the upper sum and the lower sum, the difference between the upper sum and lower sum gets smaller than epsilon, which means the function f is integrable or Stieljes integrable with respect to sum of two functions, G1 and G2. Okay. So far, we only proved the integrability, the Stieljes integrability with respect to sum of two functions. We now verify this equality. Okay. So to prove this equality, let me compute. Let me start with the reference line. So Stieljes integral of function f with respect to sum of two functions, G1 and G2. Okay. This is Stieljes integral, which agrees with the upper Stieljes integral or lower Stieljes integral. If you compare this against the particular upper Stieljes sum, the integral, upper integral is the infimum of all possible upper sums. Give me a second. Okay, so a particular upper sum is greater than or equal to the upper integral. And for here, the partition P is chosen from this estimation. The difference between the upper sum and the lower sum gets smaller than epsilon, which means the upper sum can be bounded by less than or equal to the lower sum of function f over this partition plus the arbitrary constant epsilon. Okay, then this is the same. This lower sum can be split into the lower sum with respect to G1 and the lower sum with respect to G2 and plus that. Now, what about the Stieljes integral with respect to G1? Okay. The Stieljes integral of function f with respect to G1. This could be the lower integral, lower Stieljes integral, which is the supremum of all possible lower sums, which means this integral is greater than or equal to the particular lower sum. And similarly, this part can be replaced by the Stieljes integral with respect to G2 and plus epsilon. However, this epsilon is arbitrary. Since this epsilon is arbitrary. This inequality holds, this inequality is true without this epsilon. So the integral with respect to G1 and G2. The sum of two functions is less than or equal to the sum of two individual in Stieljes integral. Okay, so we proved this part, this inequality with this direction. And for the other direction, we're going to repeat the similar arguments for the other direction. Excuse me. Starting from the same Stieljes integral, this is the Stieljes integral. So it gets bigger, greater than or equal to the particular lower sum with respect to the sum of two functions. Okay. Again, this the lower sum is greater than or equal to the upper sum. Minus x. Okay. Here, partition P was the one that we have constructed before. The difference between the upper sum and the lower sum gets smaller than epsilon. Okay. Then again split this upper sums into two parts. The upper sum with respect to G1 and the upper sum with respect to G2. Then minus epsilon. So we have this inequality against the Stieljes integral. Okay, the Stieljes integral is the infimum of all possible upper sums. And similarly, this part can be replaced by the Stieljes integral with respect to G2. Again, this epsilon is arbitrary. Okay, so this inequality is true with the epsilon on this side, which means this inequality is also true without the epsilon. So we have inequality with the other direction. So this Stieljes integral is greater than or equal to the Stieljes integral with respect to G1 and the Stieljes integral with respect to G2. Okay, so we verified two inequality with different signs to different directions to get the equality between them. Okay. All right. Now Can we consider the function g of x, which is a constant? The Stieljes integral with respect to a constant function. What could it be? The Stieljes integral with respect to a constant function. Then, for any upper Stieljes sum or lower Stieljes sum, the increments delta z is always zero. Okay, so for the constant function, Stieljes integral with respect to constant function is zero. However, what if the function g has a some discontinuity? So let me define the function j sub u of t. It is a jump function at u. That means this function is like this. At u from the variable t. This function has value 0 up to here. Then suddenly it changes value to number 1 at this point. So it's a natural jump function of size 1 at the value t, value u, which means this function has has the value either 0 or 1. If t is less than u, the value of the function is constant 0. And if the variable t gets bigger than, greater than or equal to u, the value changes into 1. Okay? Especially j at 0 of t is called h of t. It's called Heaviside function. Actually, this jump function ju of t is simply the translation of a Heaviside function. The Heaviside function is the standard jump function at 0. It has value 0 here and changes value to 1. This is a Heaviside function. So the natural jump function can also be understood as the translation of Heaviside function. P minus u. Okay, anyway. This jump function is also an increasing function. We may consider the Stieljes integral with respect to jump function. The function f is bounded. The domain of definition, and u is a point in this domain of definition. Here, we are shown function f is continuous. The continuity at the point u. If that's the case, the Stieljes integral of this bounded function and continuous function at this point, jump point, the Stieljes integral of this function with respect to dju, the jump function at u. What could it be? It's kind of surprising, isn't it? The Stieljes integral actually pick up the value of the function at u. Okay, so say suppose we have a function f like this, at some point u. For the Riemann integral or Davo integral, this is a very unusual situation. The integral, okay, let's consider the Riemann integral of function f with respect to t. Okay, and if we change the value of function as somewhere else, Okay, this is function f tilde. The single value of the function at a specific point does not affect on the integration. The integral of original function is the same as the integral of f tilde for the Riemann integral. Okay, the Riemann integral does not depend on the value at a particular point. However, the Stieljes integral with respect to jump function actually pick up the value at that point. Okay, that's very unusual, very unusual situation for the integration. Okay, let me explain the reason. Consider a partition P, okay, which is A, is T0, and T1, okay, this looks better, into T0, T1, T2, and T3. Okay, this is A, and this is B. Then what about this T1 and T2? On this interval from A to B, we have a jump point U. Okay, then T1 is chosen U minus delta, right before the jump point. And similarly, T2 is chosen as point U plus delta. Okay, so this T1 and T2 gets very close to jump point U. Okay, then we're going to consider the increments of this jump function. They have three different intervals in this partition. The first partition increments in the first subinterval, which is J U at T1 minus J U at T0. This jump function has value 0 before the jump, so those two values are 0. So there's no increment. Then the increments of this jump function 2 and 3, which means the increments of jump function at the second of interval from T2 minus Ju of T1. And this one is the increments of jump function for the last subinterval T3 minus Ju at T2. Again, this term is 0 because both of them are number 1. Okay. However, the increments in the middle subinterval from T1 to T2, the jump function has value 0 for T1 and the value 1 for T2. So the increment for this small interval, for the middle interval, is number 1. Okay. From this observation, what about the Stieljes sum of function f with respect to jump function? Here I'd like to denote the partition P as P delta that depends on this delta. Okay, so partition P delta. Okay, for this partition, I have a 3 subinterval. So the upper sum should have the 3 different terms. However, those 2 terms has 0 increments. We only have the middle term, which is the supremum of function f over this small subinterval from u minus delta to u plus delta, multiplied by the increments of jump function, which is 1. Okay? And similarly, the lower sum of function f with respect to jump function, p delta, will be the impimum of this function. from u minus delta and u plus delta. Okay. Now, what if we take the limit? The limit, as delta tends to zero. The limit, delta tends to zero. Then the supremum of this function on the small interval from u minus delta to u plus delta will converge to f of u. And the infimum also converges to f of u. Why? Since the function f is continuous at u. Okay? So they agree. They have the same value. The upper sum and the lower sum meets at this way. If that's the case, the upper sum, upper integral, or upper Stieljes integral must be the limit of the upper sums, and the lower Stieljes integral must be the limit of the lower sums. So they agree with the same value u. Okay, that's the way to handle the Stieljes integral with respect to jump function. Okay, now there's another important method or important property for the Stieljes integral that enables us to compute various Stieljes integral, which is the case when g is a C1 function. Now f is a continuous function on a closed interval from a to b, and g is C1 function. So we can take the derivative of this function, and the derivative g prime is also continuous. And the Stieljes integral of function f, a continuous function with respect to g1 function. This can be computed in this way. First, f of t with respect to the g of t. Okay, and we just skip the name of the integral variable t. So let me specify the integral variable. Then you can simply, symbolically, this is true. You can divide this by dt and multiply dt. What does that mean? This is the same as the integral ft or f, the function f, multiplied by g prime. So this is the derivative. Okay, we can replace the Stieljes integral with respect to C1 function g into the Riemann integral. This is a simple Riemann integral, right? A Riemann integral of function f multiplied by g prime. Okay, why? Here, f, both f and g prime, both of them are continuous, which means their product f times g prime is also continuous. And our continuous function is integrable, so this is integral. And the function f, this function, a continuous function, is still just integrable with respect to function C1 function g. So this is a g integral. And for any positive epsilon, there exists partition P. there is a partition P is T0 and T1 up to Tn such that, okay, for arbitrary epsilon, since f times g1 is integrable, which is the Riemann integrable, okay, we can choose the partition P such as the upper sum, the upper sum of function f times g prime over partition P and the lower sum of f times g prime over partition P that's smaller than f of epsilon. Okay? At the same time, this function f is g integrable, which means for this partition, the upper sum of function f with respect to function g, the Stieljes sum, and the minus the Stieljes sum that's smaller than half of epsilon. Okay? Of course, to begin with, these two partitions, this partition should be different from the partition for this inequality. However, you can take the union. Okay, here at first, this partition must be P1, and this is another partition P2. Okay, but by taking the union of those two partitions, we have the same partition P. We have the those two conditions true for the same partition P. Now we're going to apply the mean value theorem to the C1 function G on each subinterval. Each interval from tk minus 1 to tk, which means there exists xk on the subinterval from tk minus 1 to tk, such that g of tk minus g of tk minus 1, the increments, divided by the length of the interval is the same as g prime of xk at some point. Here I'd like to move the denominator to this side, tk minus tk minus 1. Okay? This is the increment of function g that we're going to use for the definition of Stieljes integral, which can be replaced by g prime at some point multiplied by this one. So can you see the relation between the Stieljes integral like this and the Riemann integral with g prime in here? Okay, so the Stieljes integral, we essentially compute the summation like this. As k goes from 1 to n, for each subinterval, we evaluate the function f at some point multiplied by the increments of function g, g of tk minus g of tk minus 1. Okay, which is the same as the summation f at xk multiplied by g prime at xk, tk minus tk minus. From this equality, if you replace this part by the supremum of function f on this subinterval, you're going to get the upper Stieljes sum. And you can replace this part by the supremum of f and g prime, f times g prime on this subinterval. We're going to get the double sum of function f times g prime on the subinterval, on the partition P. Okay? For this observation, we can compare the lower Stieljes sum. Okay, I'd like to take what if we replace this sum, this value f as substitution point xk by its impute, you're gonna get the lower Stieljes sum. And if we replace this part f of xk times g prime at xk by the supreme. Then it gets bigger, which means the lowest Stieljes sum, like this, is less than or equal to the upper Riemann sum or upper double sum of function f times g prime at p. Right? And at the same time, what if we take the infimum for this part, which means the lower integral, no, the lower sum of f times g prime over partition P gets less than or equal to. Now, if we replace this term by its supremum, we're going to get the upper Stieljes. Okay? Then we can combine those two inequalities to get, okay, let me start with the left-hand side of this inequality. Stieljes sum. The Stieljes sum, no, I should say Stieljes integral. The Stieljes integral of f with respect to g is less than the upper Stieljes sum with respect to specific partition. Then the upper Stieljes sum is less than the lower Stieljes sum plus half of epsilon. Okay. Then this lower Stieljes sum can be bounded by the upper sum of f and g prime plus f of epsilon. Now what about this one? The upper sum of f and g prime is bounded by the lower sum plus f over. This is again bounded by the lower sum of f and g prime and p, and plus another f over epsilon. Okay. Finally, the lower sum of f and g prime is less than or equal to the lower integral or the integral of the product of two functions f and g prime. Okay. Again, the choice of epsilon is arbitrary, so this inequality is true without the epsilon. Since epsilon is arbitrary, the Stieljes integral of function f with respect to g is less than or equal to the Riemann integral of f times g prime. Okay. And you can also prove the inequality with the other direction by similar method. You start from the Stieljes integral is greater than or equal to the particular lower sum. By similar argument, can prove the inequality with the other direction. The Stieljes integral with respect to g is greater than or equal to the Riemann integral, the product of f and g. Okay. So this is very nice property for to compute the particular Stieljes integral. For example, now we are ready to compute the integral, the Stieljes integral of function x with respect to x squared. Take the example that we have started in this lecture. What's that? This is the integral of x times the derivative of x squared, which is 2x. Okay? Or this could be 2/3 in x cubed. That gives us 2/3. Okay? So this is the way to compute the Stieljes integral with respect to a C1 function. Okay, that's pretty much the everything that we're going to learn for the Stieljes integral. Okay, thank you.